This webinar focuses on the role of Antarctica in the global climate, long-term impacts of short-term decision-making. My name is Kylie Owen, and I'll be the moderator of today's session. I'm a marine mammal expert and an officer for the European Polar Board and the European Polar Coordination Office. Ocean Ice is a Horizon Europe project. It is funded by the European Commission and UKRI. Ocean Ice assesses the impacts of key Antarctic ice sheet and Southern Ocean processes on planet Earth via their influence on sea level rise, deep water formation, ocean circulation, and climate. Within Ocean Ice, the European Polar Board leads the webinar series, presenting the objectives and ongoing developments across the project's work packages. Today, our webinar focuses on Work Package 6, that investigates how changes in Antarctic freshwater fluxes, including those from melting icebergs, affect the global climate system with the use of coupled ice sheet, ocean models, and Earth system models. We are delighted to have a great lineup of speakers today. We have Tony Payne, who's from the University of Liverpool, who will introduce the program. We have Jing from the University of Liverpool, presenting regional ice-ocean feedbacks in a global Earth system model. Yavor Kostov from the British Antarctic Survey, and Robin Smith from Reading University, sharing insights on the impact of icebergs and ice shelf collapse in climate modelling simulations, and Torsten Albrecht from Potsdam Institute of Climate Impact Research, presenting long-term effects of global warming on the interaction of Antarctic ice sheet, ocean, and solid Earth dynamics. Please post any questions you have in the chat during the talks. We'll take 1 or 2 short questions after each session and then return to a more detailed Q&A at the end of the webinar. So with that, let's get started. I would like to first invite Tony to introduce Work Package 6. Tony is a Professor of Earth, Ocean and Ecological Sciences at the University of Liverpool. Tony's research focuses on understanding the past and contemporary behaviour of ice sheets and predicting their future change. This is done through the development and application of numerical models of ice sheet mass budget and dynamics to predict sea level change. Tony co-leads with Torsten Work Package 6. So Tony, the floor is yours. Thank you.
Great, thank you very much. Let me just sort out the sharing. Hopefully I get this right. Okay, can you see the screen?
Yes, we can.
Yeah, great. Okay. Okay, well, thanks for that great introduction, Kylie. So I think you've pretty much covered much what's on this slide, so I'll skip on. As I guess the majority of the audience are very well aware, there's a lot of evidence that the ice sheets are losing mass and have been for the last few decades, and all projections share in common that this mass loss is going to increase significantly over the coming centuries. Up until Ocean Ice, really, most of the research was focused on the implications of this mass loss for sea level rise. Obviously, that's a very direct impact of the ice sheets losing mass, but it's not the only impact. So Ocean Ice in particular is more interested on the impacts of the fresh water that leaves Antarctica in particular, and how that may affect global climate and in particular the ocean. So we're trying to move away from just this focus on sea level rise and looking at the impact of this huge volume of fresh water being released from the ice sheets on the global climate system itself. What's interesting is that for sea level rise, many of the effects are mitigated by the fact that you get mass loss, yes, because ocean is warming, but also for Antarctica in particular, you get increased snowfall because the atmosphere is warming as well and carries more moisture. Obviously, for freshwater fluxes, we don't have this mitigation. So what you're looking at is just a couple of examples. Firstly, from the most recent IPCC assessment demonstrating that this rise in global sea levels. Then more pertinent to us is results from our colleagues in Work Package 4, in particular Vio Coulon, and her projections of mass loss from Antarctica for the next 300 years or so. And you can see from this latter plot, the lower one, that subshelf melt, the melt of the ice shelves, in particular around Antarctica, is projected to increase perhaps at least by a factor of fivefold, perhaps even up to a factor of tenfold. So that's it's certainly true that there will be a major reorganization of the oceans around Antarctica as a response to this huge influx of fresh water. So I like to characterize this diagram as a toppled Christmas tree, and work package 6 sits at the peak of the Christmas tree, and it's either the little white angel or the star that sits at the top of the Christmas tree. You can see in this diagram that as you progress from the left to the right, there's a focus, and you would have heard of this in previous seminars, on process understanding. And as you gradually move through the work packages, through 4 and 5, that turns into a focus more on what happens to the fresh water and what are the impacts on the ocean and the ice sheets. And then our work package in particular focuses on, given this mass loss, how might it affect global climate? So here's a very short definition of what we're supposed to have or be doing in the work package, and that's assessing the impact and feedbacks between global climate metrics, such as sea level rise, we've talked about, but also other things like global mean surface temperature and various measures of the carbon budget of this melt. So it comprises 4 partners, which is the Potsdam Institute for Climate Research, PIC, British Antarctic Survey, so it's PIC, and then 3 UK partners, British Antarctic Survey, University of Reading, and Liverpool. And we have representatives from each of those partners here. So we share in common that we're all using coupled models of various sorts, and the modus operandi of the work package is to use these coupled models to simulate the effects of this freshwater release. We use slightly different models, and you'll hear more about that in the presentations. But essentially, you have 2 flavors. There's the groups, primarily the UK groups, using UKESM, and I'll describe that in a minute, which is a large-scale Earth system model which uniquely has coupled ice sheets within it. We'll be using UKESM to look at the impacts of freshwater release. And that's on the relatively short timescales of up to 2300. And then PIC, and Torsten will talk about this in particular, is exploring the longer term impacts beyond 2300, where feedbacks between the ocean and the ice sheets become important, as well as feedbacks with the solid Earth. And the PIC group use a coupled ocean ice sheet model called PISM-MOM. So just to briefly outline the talks that you'll hear today, these are very well aligned to the 3 tasks that the work package has. The first task, 6.1, is to look at freshwater and iceberg fluxes from Antarctica into the global model. Yavor will be describing his work on the impact of icebergs on the Southern Ocean. The second task is to look at Earth system impacts up to 2300, and there'll be 2 talks on this task. One from Jing, who will be looking at regional ice ocean feedbacks in the global model, and then Robin will describe initial simulations of ice shelf collapse within UKESM. And then the final talk relates to the last task within our work package, which is these longer term millennial scale impacts. So before I hand over to, I think it's Jing, I thought because UKESM is used by a large number of a lot of the work package, I thought I'd just give you a brief introduction to UKESM. So UKESM is the UK's Earth system model and participates in the usual sort of climate assessments, such as the ongoing CMIP exercises that then contribute into the IPCC. It contains a couple of components, all of the Earth system. So we have the ocean is represented by the NEMO ocean model, the ICE sea ice model, and also includes marine biogeochemistry via Medusa. The key thing with the ocean model is that it includes the ice shelf cavities, the ocean cavities underneath ice shelves. So it's actually calculating the circulation of the ocean in these cavities, fluctuations in that circulation, and its impact on melt. The next component is the atmospheric one, and it contains the Met Office's atmosphere model as well as a full atmospheric chemistry model. And then on the land surface, we have the JULES land surface physics model that deals with hydrology, and that's coupled to biogeochemistry and dynamic vegetation model. And then the key thing for us is that it's also coupled to what we're calling unicycles here, or the BISICLES ice sheet model, which has two separate configurations, one for Greenland and one for Antarctica. So for Greenland, the coupling is primarily to the atmosphere and to the land surface that calculates snowfall and snow melt, but also to NEMO, and that's what Jing in particular will be focusing on, the coupling between the ice sheet and the ocean. The runs that you'll be hearing today are part of a large ensemble that has been run by UKESM and is also being run by a number of other Earth system models. And the design for this is fairly simple. So we have a pre-industrial control where we're setting global carbon emissions to pre-industrial levels. We then have a ramp up, which a constant rate of anthropogenic CO2 is added to the atmosphere. And this is around 8 gigatons of carbon per year, which results in a fairly uniform rate of global warming, which is 0.2 degrees C. Then at various points, we branch off experiments at fixed global warming levels, say 2 degrees C. We cut the emissions and we run at zero emissions forward in time. And then at some point, you may hear some of the experiments being described where we reduce global CO2 by extracting it from the atmosphere. So that's the basic design. And that's, if I just talk through these various panels, the first one is just the accumulated carbon within the system, which is as I described. The second one here is the atmospheric carbon dioxide, and you can see that although the total amount of carbon in the system follows these very straight lines, the amount of carbon in the atmosphere varies a lot, even when we're reduced to zero emissions. That's because of the absorption of carbon in the oceans and on the land surface. These are the equivalent global mean warming levels. And then, again, you can see, interestingly, that although we're holding the atmosphere, the emissions at zero, there is global warming still going on as a response to past emissions of carbon. So what we're really interested in is the impact of these levels of warming on Antarctica and its mass loss of freshwater loss from Antarctica. So now we're comparing on the left time series of the global mean warming in these various experiments with what's going on in Antarctica. And you can see that immediately that Antarctica's response to this relatively uniform global warming is very step-like and non-linear. So we have these abrupt jumps in the melt rates. And Jing in particular will talk about why these are occurring. So you can see, for instance, if I pick out, let's say, the 4 degrees C global stabilization experiment here, where are we? 4 is over here. Sorry, the color scales are a bit wrong. 4's over here, so relatively uniform global warming, but we have these step changes in the amount of fresh water leaving Antarctica. And this is just to give you an idea of where that fresh water is coming from. So this is for the ramp-up experiment, which is this red line on the left-hand side, which is the experiment where we've got constant emissions of carbon into the atmosphere. And you can see that we have these step changes, as you saw in the previous diagram, of the melt rates. And in particular, now so this is the overall melt rates of freshwater flux leaving Antarctica. And you can see that these two steps that characterize what's going on, one's something happening in the Ross cavity, and then some few hundred years later, the same thing seems to happen in the Ronny-Filchner cavity. But Jing will talk a lot more about these in detail. Okay, that's hopefully an introduction to the work package, and in particular to UKESM and the way in which we're going to use UKESM. Very happy to take questions.
Yeah, thank you very much, Tony. It was a very nice introduction, and yes, very handy to get an introduction to the UKESM as well. We're now moving on to the second part of the webinar that is related to regional ocean ice feedbacks. And so, as Tony hinted, the next presenter is Jing, a polar oceanographer and climate modeler and postdoctoral researcher at the University of Liverpool. During their PhD, Jing used a regional ocean model to understand the present and future changes in Amory basal melting. In ocean ice, Jing's research focuses on investigating the impact of freshwater fluxes from Antarctic ice loss on global ocean, and this is done primarily through the running of a coupled UKESM model with an interactive ice sheet component. Jing will present to us projections of regional ocean ice feedbacks from a global Earth system model. So I'll hand over to you now, Jing, if you want to share your screen.
Is the sharing okay?
Yep, that's perfect.
All right, thanks, Kylie, for introducing me. So yes, I'm going to give a talk about some regional ice ocean feedback in UKESM. So I don't think I need to emphasize the importance of Antarctic ice sheet. So I would like to start from why we need an interactive ice sheet component in Earth system model. So this figure illustrates the transfer processes of oceanic heat from the interior, like ocean, to an ice shelf. So we mainly care about the, laser points. So we care about the process 3 and 4. So that's the heat transferred from the interior ice shelf cavity to the mixed layer or the top boundary layer, then to the ice. So the most commonly used parameterization to describe this process in ocean models is 3-equation parameterization. So I will not bother you by the physics and equations. I just want to say there are some important variables. So I will go through one by one. The first is TB, freezing point. So it's dependent on the salinity at the ice-ocean interface and the depth of ice. So it basically describes the heat demand to melt ice. Then the second, the TB minus, or TW minus TB, thermal driving. So it's the temperature difference of seawater in the top boundary layer and in situ freezing point. So it describes the heat supply in the top boundary layer. The last one, gamma T, the heat transfer coefficient. So it shows how much heat can be transferred from the top boundary layer to the ice. So it dependent on this term, the square root CdUW. We call it friction velocity, which is related to the velocity in the top boundary layer. So the combination of these variables determine the heat actually used to melt ice. So the melting is not only sensitive to the external oceanic heat, it's also a function of the geometry of ice shelf itself. So this study show the melt rate change with the basal slope of the ice. However, most models, they just don't care about the ice shelf dynamics. For example, in standard CMAP6 model, the ice shelf cavities are closed, so nothing happens here. The fresh water from Antarctic ice sheet is prescribed, so they are not calculated online. While in some standalone ocean model, the cavities are open, so the seawater is allowed to get beneath the ice. The interactions happens at the ice-ocean interface, and the melting is calculated online, which is good. But the geometry of the ice is static, so it will not change throughout the simulation, which means it cannot capture the geometric ice ocean feedback. So that's why we need a two-way coupled ice sheet ocean model. So the ice sheet can provide the geometry of the cavity to the ocean. Then ocean calculates the basal melt rate, then feedback to the ice sheet model as a boundary condition. So in this way, we can resolve a time-involving ice shelf cavity and understand the geometric feedback. So luckily, we have coupled UKESM ice sheet model, UKESM 1.2. Thanks, Tony, for introducing the UKESM and terra firma framework, so I don't need to spend time on that. I will present two ramp-up experiments today. So one is with interactive ice sheet, and the other one is without interactive ice sheet. And we use 1 degree ocean in UKESM. So the large ice shelves like Ross and Felsenaroni are more reliable than small ice shelves. So I just will show the analysis of Ross ice shelf today because Felsenaroni is very similar to Ross. Okay, let's move on to some results. So this figure shows the time series of basal mass loss from top to the bottom is the whole Antarctica, Ross and Felsenaroni. Blue lines shows the melt rate from the interactive ice sheet run. The orange lines shows from the static ice sheet run. There are some common features, say both ice shelf tip in the two experiments, like here and here. But in the say interactive ice sheet model, the melt rates show a flip, then like flip behavior. So the melt rates peak then decline in the interactive ice sheet run. But in the static ice sheet run, the melt rate just goes up and up. So their long-term pattern are very, very different. So some people may wonder what caused the tipping here. So Caitlin Norton at SPAS, so like her 2021 paper found the freshening outside of the cavity caused the regime change of Felsenaroni. And she's also working on the tipping mechanism in the terra firma UKESM runs. So stay tuned, she's working on a very exciting paper, but my work is mainly to answer what caused the peak then decline. Then let's see more spatial features. So this is the spatial distribution of melt rates from the interactive ice sheet run on the top panel and the static ice sheet run on the bottom panel. It's very clear the melt rates, especially at the grounding line, has increased then decreased on the top panel, but the melt rate is very high, even higher with time in the bottom panel. So obviously no decline. And there's a temperature change in a transect of Ross ice shelf. We can see the warm water flash the cavities in both experiments, and there's a warm layer of fresh water beneath the ice. But in the interactive ice sheet run on the left, there's a thinning and a flattening, particularly at the grounding line. And also the basal slope becomes much smoother, like here. And the salinity change at the transect suggests a very strong freshening in the cavity and also in the shelf sea. And the cavity becomes very stratified, and there's a freshwater layer beneath ice. So now I hope you have some, general picture of what happens to ice and what happens to the ice shelf cavity. It seems the cavity is still very, very warm at the end of simulation. So what caused the melt rate to decline? We will have to go back to the 3 equation parameterization and to see what happens to the top boundary layer. Remember the variables I introduced at the beginning. So the friction velocity at top, then thermal driving mid panel. They both show a peak then decline behavior. So that explains why melt rate has a flip, because melt rate has to follow their track, right? Then the following question is why friction velocity and thermal driving decline. Let's have a look at the cavity circulation. So the top panel on the right shows the strength of the cavity circulation. So after the regime change, so the circulation strength in the interactive run has a large decline here. And this is because the stratification in the cavity reduced the buoyancy, because we know the cavity circulation is buoyancy driven, so it's losing buoyancy. And the other reason is the flattening of the ice shelf fundamentally changed the background pressure gradients, and that reduced the circulation as well. So as a result, UW decreased. Then why thermal driving becomes smaller? So firstly, TB, in situ freezing points, we know it's a function of salinity at ice-ocean interface and the depth of ice, which we know that both decrease, right? So which results in a higher in situ freezing points, means the ice requires more heat to get melts. At the same time, the TW, the temperature in the top boundary layer, is decreased because when the ice melts, so there's a new cold meltwater is added to the top boundary layer. And then the stratification in the cavity prevents the heat entrant from the interior cavity to the top boundary layer. And also, when the cavity circulation becomes weaker, the cavity is like more stationary. So this is their residence time. We can see the residence time in the interactive ice sheet run becomes very long at the end of the simulation, which means the water mass exchange inside and outside the cavity becomes much slower. So there are less warm intrusions in the interactive ice sheet run. As a consequence, the thermal driving decrease. Okay, so I'd like to make a summary. So many studies show this positive ice-ocean feedback, but with an interactive ice sheet model, we can capture the negative feedback, and then we can stop the more and more basal melting in the standalone ocean models. So I would like to stop here. Just any questions?
Yeah, thank you very much, Jing, for the nice overview of the model projections. I don't see any questions, but just a reminder, if you do have questions for any of our presenters today, please put them in the Q&A and we'll address them as we go through the webinar. We now move on to the second scientific thematic of this webinar that is related to iceberg carving and evolution with both Yavor and Robin. Yavor Kostov is an ocean iceberg modeler at the British Antarctic Survey. He has a background in mathematics with experience on studying abrupt transitions between different possible regimes of the El Niño-La Niña phenomenon, the impact of greenhouse gases, the ozone hole, and atmospheric variability on the Southern Ocean and beyond, ocean circulation and water masses in the North Atlantic as well. Within ocean ice, Yavor models iceberg dynamics and iceberg grounding in the Amundsen Sea using the NEMO ocean model. So today, Yavor will talk about the impact of icebergs on the Southern Ocean in UKESM climate change simulations. So I'll hand over to you, Yavor.
Thank you so much. It's a pleasure to be here once again. And I just want to mention that this work that I do at BAS is supervised by Paul Holland within Polar Oceans. And indeed, I'll talk about the impact of icebergs on the Southern Ocean in some idealized UKESM climate change simulations that follow the same protocol that Tony and Jing outlined earlier. So I won't go over that in detail again, but I'll say that the work that I'll present now focuses mostly on output from an idealized CO2 ramp-up experiment where the concentration is continuously increased. But at the end, if there's time, I'll also hint to some early results from experiments where the CO2 concentration is decreased. In this fully coupled ramp-up experiment, we have this almost linear rise in the globally average surface air temperature compared to the control simulation. And throughout the course of this warming experiment, we see changes in the pattern of where Antarctic icebergs melt. Red shading in this plot indicates areas where we have a negative trend, a reduction in the iceberg freshwater fluxes into the ocean during the ramp-up simulation. And blue shading highlights areas where we have an increase in the amount of meltwater from icebergs to the ocean. This dipole pattern indicates a shift to higher latitudes. So we have more icebergs melting at the higher latitudes near Antarctica and fewer icebergs melting away from Antarctica in the open Southern Ocean. This is important because the densest, deepest layers around Antarctica reach the surface and outcrop around the continent on the shelf. And these deepest, densest layers are quite important in the context of present-day climate change in the real world, because almost 90% of the excess heat in the system is stored in the ocean, and out of that, about 10% is stored below a depth of 2 kilometers, meaning that almost 9% of the excess heat under climate change is stored in the densest and deepest layers that outcrop at the surface near Antarctica. So let's have a look at this trend in the shift of iceberg melt pattern in density space. Instead of plotting things spatially, we look at the trends relative to different density layers, where we've assumed that the density is the one that water would have if it was brought down from the surface to a depth of 3 kilometers, and we call that sigma 3. So this potential density space shows that we actually have an increase in the iceberg meltwater at lighter densities and a decrease at higher potential densities, which is somewhat surprising because we expect that around the continent we would have larger potential density, and we see an increase in the meltwater there. So how do we reconcile this spatial shift with the shift in density space? To do that, we have to look at how the surface pattern of potential density changes throughout the ramp-up simulation. And we focus on the Southern Hemisphere winter. So, for example, August would be a winter month in the Southern Ocean, because that's when we have this deep mixing in the upper ocean that allows the signals to be communicated from the surface to depth. And in the first August of this ramp-up simulation, we have this pattern of potential density at the surface, while in the last August of that ramp-up simulation, if we use the same Cowher scale, we don't see these dense layers outcrop. We have to shift the Cowher scale to see that we end up with a very different pattern of density at the surface. And this shift in potential density outcompetes the spatial shift in where icebergs melt. And this has implications for the amount of iceberg meltwater that reaches the deepest, densest layers around Antarctica all the way to the abyss. So let's have a look at how these changes are communicated down to depth. To do that, we'll make use of a concept called neutral density in the ocean. If you imagine two water parcels with different temperatures and salinities located at different depth and pressure in the ocean, we know based on fundamental physical principles that they'll tend to move relative to each other in such a way that gravity and buoyancy do minimal work. That means that these water parcels would try to stay surrounded by water parcels of the same density. But if we move that parcel above downwards to a greater depth, under this increased pressure, it feels its density will increase. And similarly, if we move the deeper water parcel up to a lower pressure, its density will decrease. So it's possible to bring together two water parcels in such a way that if they meet halfway through at the pressure level in the middle, they will have the same density at that pressure level. They would be neutrally buoyant with respect to each other. And even though this is an idealized concept, we can construct approximately neutral surfaces that connect the upper ocean to the abyss in the Southern Ocean. And there are different ways to achieve this approximation, gamma surfaces, and this is one way to approximate these neutral density surfaces called an omega surface. And this particular omega surface along a section in the control simulation shows how we can move water parcels from the upper ocean all the way to the abyss in such a way that they remain neutrally buoyant. And if we plot the spatial pattern of the depth of this surface, we see that it's very close to the air-sea interface along the shelf, but also in some locations in the open ocean, where we think that the model represents openings in the sea ice cover called polynyas. And if we oversaturate the cover scale, we can highlight the particular areas where we have this potential density surface come close to the air-sea interface. In the ramp-up simulation under CO2, these outcrop regions shrink spatially and shift. But we also care about the concept of enhanced wintertime mixing in the upper ocean that allows these surface signals of warming and tracer changes to be communicated to depth. So we care about the depth of this surface mix layer in the ocean. And both in the control and the ramp-up simulation, we do see mixed layer depths in the winter, the Southern Hemisphere winter, on the order of several hundred meters, in close to the regions where this neutral density surface outcrops. So if we superimpose the climatological August mixed layer depth and the location of this climatological neutral surface, we see that they come close to each other near the coast. But there's a lot of temporal and spatial variability. So we have a spread in the depth of this surface and also a spread in the depth of the mixed layer in the winter. And we're actually interested in all possible locations where this deep layer comes close to the base of the surface mixed layer. Excuse me. And this plot shows the locations where this deep neutral density surface gets in contact with the mixed layer in the control simulation in August, and the same plot can be seen for the ramp-up simulation month by month for the full ramp-up simulation. Towards the end of the ramp-up simulation, this area where we expect the abyss to have a conduit to the surface shrinks, mostly to these open ocean polynyas or areas of low sea ice concentration near Maud Rise in the Weddell Sea. So going back to our earlier plot where we looked at things referenced to a pressure at the depth of 3 kilometers using density as if we were at the depth of 3 kilometers, we can see that there was this decrease in the amount of iceberg freshwater supplied to these potential density levels, and similarly neutral density space, where we build this mathematical construct connecting the surface to the abyss, we see a comparable trend in the amount of iceberg freshwater that reaches this omega surface. And my ongoing work now is to compare how symmetric or asymmetric and reversible or irreversible these changes in the CO2 ramp up run are compared to changes that we see in ramp down and stabilization experiments, whether we have some degree of irreversibility or at least some degree of inertia in the system where it takes a long time to recover the previous state. So just to summarize, I have been exploring the anomalous iceberg melting trends under idealized CO2 ramp up in this coupled configuration, and exploring this dipole in the shelf versus open ocean pattern of iceberg meltwater, where we have competition between the spatial changes in where iceberg meltwater is released and the density space changes, both in potential density and neutral density space, seeing some potentially significant shifts in this pattern of where iceberg meltwater is supplied to the deepest, densest there around Antarctica, which is a precursor to what we call Antarctic bottom water, or ABW. So thank you for your time, and I'm looking forward to questions and discussions.
Thank you, Yavor. I'd now like to invite Robin. Robin is an associate professor at the National Centre for Atmospheric Science at the University of Reading. Robin is part of the core team of scientists and developers working with UKESM and leads the work to improve how we model ice sheets and polar climate in UKESM. Robin has a broad interest in topics related to large-scale climate and how different parts of the system interact, especially around land ice and sea level. In Ocean Ice, Robin is investigating the potential large-scale climate impacts of future freshwater and sea and ice release from the Antarctic ice sheet. Robin's presentation focuses on the initial simulations of the climate impact of ice shelf collapse in the UKESM. So I'll hand over to you now, Robin.
All right, thanks for that introduction, Kylie. So, all right, yep, I'm going to talk about some work that Steve and I have been doing in Ocean Ice on modeling and understanding physical processes about how some big Antarctic freshwater flux releases might affect the wider climate Earth system. So this is going to be a bit of a step back from the level of detail that Jing and Yavor have been showing us. This is going to be like a big experiment, a big hammer to hit the Earth system with, let's say. So I don't really need to motivate sea level rise for anyone watching this webinar, I guess, is like a big impact of climate change. But I think it is worth showing a plot like this to show the huge uncertainty that there is around what sort of level of sea level we might get off Antarctica, and also the sort of the rate of sea level rise that we might get from Antarctica. And these really come from just sort of the potential for really big, abrupt, catastrophic events happening on the Antarctic ice sheet, sort of flips to completely different states or large amounts breaking off. And we're pretty limited in our physical understanding of when those might happen, what might trigger them, and really in any kind of capability for projecting what happens to the rest of the Earth system when that happens. And I'll talk a little bit about why that is in a minute. But it's also worth pointing out, maybe for this audience in a European context, that ice mass that comes off Antarctica sort of disproportionately affects the northern hemisphere and Europe compared to the rest of the world because of some of the solid Earth and gravitational feedbacks. So we really should care about loss of ice from Antarctica. It's not just this very remote place at the other end of the world. So for some of these like major sea level things to come from Antarctica, what it really needs is for some of these ice shelves that Jing was talking about to disappear. That either means melting from below or potentially ponding or something causing mechanical breakage at the top, or just a very large calving event, cliffs collapsing, something like that. So those shelves themselves don't affect sea level rise, but what they are doing is holding back the ice that's on the land. And they have this buttressing effect. So to get those really big contributions to sea level from Antarctica, we need to get rid of those ice shelves and have them allow the ice to flow off the grounded portion of the ice sheet. So getting rid of one of those ice shelves doesn't just affect the flow of the ice, it completely or potentially radically restructures the coastline around Antarctica. It affects what the atmosphere above sees, how that's going to transport snow into the interior, weather patterns, and it's going to be a massive flux of fresh water into the ocean around Antarctica. So it's going to be a big perturbation to the ocean circulation as well. So one of the best examples of where this happened before, on a much smaller scale than I'll be talking about, is where the Larsen B ice shelf collapsed about 10 years ago. And over the course of about a month, you can see we've got a radically different coastline. Where we had solid ice shelf before, we've now got this mass of bergy bits and sea ice, and that's going to float off into the ocean, into the Southern Ocean around Antarctica, and have impacts on the ocean circulation there. So you can see there's a lot going on. There's potential for lots of different parts of the Earth system to interact and affect each other. And there are impacts that we want to be able to model, both for the ice sheet and for the climate system around. So that's what we're looking at in ocean ice here. So, as I mentioned before, we don't have a lot of capability for projecting and modeling these things in an integrated sense that lets all of these processes interact with each other. There's a couple of reasons for this. Some of it is simply that some of these physical processes we haven't ever really observed happening. We know there's potential for them. We've got a very good physical understanding of what might happen, but we don't have lots of observations of them actually happening that we can use to build sort of reliable models or tune our models so we can tell when they will happen. So that means we have certain processes that aren't in our models or aren't in our models very well. So say fracture of the surface of the ice shelf from hydrofracture, or what happens when you've got a whole basin choked with sea ice. How does that sort of free itself and float out into the open ocean? So there's a lot of uncertainty on that part, but there's also a problem with just how we've built our Earth system models. So you've seen a couple of schematics of UKESM before, and the idea that we've got all these boxes connected by arrows, basically, and each of those boxes represents a different part of the Earth system, either the atmosphere or the sea ice or the ocean. And then we have these coupling strands between them. So one of the problems with something like ice shelf collapse is that we're not just sort of affecting physical processes within one box. We're having to have those boxes talk to each other, and because we're taking away parts of the surface, we're also taking away how those models need to communicate with each other. There's now a whole extra area where the sea ice can populate or where the atmosphere might need to talk to the open ocean. And that just isn't how we've built those Earth system models at the moment. They're designed to have sort of fairly static paths of communication between those boxes. So UKESM is a lot more advanced than some of the other models in terms of how we can model the climate around the ice sheets. Jing's told us about the cavities, Yavor's told us about the icebergs, but we do still have some of those structural limitations in how these different components can communicate with each other. So in the last year of Ocean Ice, Steve and I have been working on that and how we can make those more flexible and do some UKESM simulations where we do actually take the ice shelves out properly. So I'm not quite going to be talking about that, but I'm going to be talking about something that's an important step towards having those simulations run. So as Jing showed us, we've got UKESM simulations where you get climate warming, you get a flip of the Ross ice shelf. So it goes from a cold shelf to a warm one where we've got lots of melt underneath it. Also in those situations, we start getting a lot of surface melt happening. So from warming, and that would lead to the potential for ponding that might also break up the ice shelf. So the storyline we're going with here for our simulations is the collapse of the entire Ross ice shelf. So what we would have to do if we did that in UKSM is we'd have to do something with that ice shelf when we take it away. We can't just magic, well, we could magic it into thin air, but we don't want to. We've got to put that mass somewhere. So what we're going to do in UKSM is we're going to put the mass of the entire Ross ice shelf into the iceberg system that Yavor was talking about. So that's a lot of icebergs. The Ross ice shelf is about the size of France or Spain. So we're generating a huge area of icebergs, and it's an amount of water that's equivalent to sort of 3 or 4 Amazon rivers sort of suddenly discharging into one basin. And that's on top of the melt that we've already got going on. So before we get to the point where we can actually take the shelf out of the UKSM simulation, we wanted to ask the question, can we actually cope with the bit where we put that mass into the icebergs? Can the UKSM iceberg system cope with that? And then what happens when we give it that massive perturbation? So we've done a fairly short simulation at this point. We're extending it a bit longer, but we've got a few years already where we've done this. So we've taken the whole Ross ice shelf, and we've thrown it into Yavor's iceberg system to see what happens. So the plot here, we've got this little block. So we basically create all these icebergs over the course of a year around the front of where the current Ross ice shelf is. And hopefully this should play a little animation you can see. So this is the amount of additional melt that's coming from those icebergs as we step through about the first decade of the simulation. And it should loop so you can see it again. You can see in the first few years, we just had this massive plume of iceberg melt coming off the front of the Ross ice shelf. And then as it goes on, it makes it so a lot of it stays fairly confined to the coast. So that's going to be providing additional sort of freshwater surface forcing as you come around the coast past the Amory in front of the Filch and Ronnie. And then after a few years, you can see it does get swept out into the ACC with the potential for causing some more sort of impacts further out into the ocean. So how much water is that? It's a lot. So you can see, so this isn't the amount we're putting. This is the amount of melt that's coming from the icebergs once they start melting. So you can see basically, so we put all the icebergs in over the first year. That's this first massive spike here. That's then the very high amount of melt is sort of sustained into the second year, but fairly quickly drops off after that. So once you get into the third year, you haven't got this massive melt perturbation anymore. We've got rid of a lot of those icebergs, but we do still have several times the background amount of icebergs then persisting in the system and slowly releasing their melt over the next few years. It's enough to sort of completely. So you can see we've got a background simulation here, which I should have talked about before. Sorry. So this is all done against the background reference pre-industrial control climate of UKSM, and you can see in there that we've got the seasonal cycle of iceberg melt in the summer and less in the winter. So we've still got, even after 5, 6, 7 years, we've still got enough icebergs in our system that melting year round, they're still sort of drowning out that seasonal cycle. In terms of the amount of water, so there are other protocols, other experiments that are looking at Southern Ocean melt in Earth system models. So say the Sophia one, they tend to release much, so their simulations of the amount of water you'd get from an ice shelf collapse is maybe 0.3 sphere drops sustained over quite a few years. So in terms of the collapse that we've got in UKSM, that's much more sudden. It's a much bigger but shorter perturbation. So what does that actually do in the system? So the basic things we expect from putting this much fresh water into the Southern Ocean is that we should get capping at the surface, so it'll become more stratified, and we'll get cold water trapped at the surface and an expansion of sea ice. So we do indeed see this. So the red line here is the sort of the background pre-industrial. The grey shading is 2 standard deviations of annual variability on top of that. And then the blue line is our perturbation experiment. So we've got so we've got this cooling that ramps up over the first 4 or 5 years, and a very significant expansion in the amount of sea ice that's mostly concentrated out in front of the Ross, and then round into East Antarctica after that. Oh, I shall speed up a little bit. And indeed, we see a massive cooling perturbation that goes with that. So these are surface air temperatures. The time series is over the whole of averaged over the whole of the southern hemisphere. And this map plot here is just from that coldest year, that very coldest year there. So we've got cooling of 9-10 degrees over bits of the Antarctic continent. It spreads all the way around, so it's affecting Amundsen and Bellingshausen as well. It's a shorter time series. So the cooling does persist at this lower level, sort of out on the sort of decadal timescale after that. There's some hint of maybe some things happening with teleconnections up to the north, but that's very difficult to assess the significance of in a simulation like this. So we're going to leave this running a bit longer and see how far that perturbation might spread. Right. So one thing we're interested in is when one of these shelves collapses, what does that mean for the rest of the ice sheet and some of the other basins? So as Tony said, our projections of Antarctica are basically based on sort of melt. Well, as it warms, you get melt from below, but you get increased precipitation, and that offsets some of the mass loss. So what we would actually expect with this cooling is that we might see a reduction in some of that precipitation, or the extra precipitation we'd get. And that's actually what we see at least over the first few years of these simulations. So again, when that cooling perturbation is largest, if we've collapsed the Ross ice shelf and released all these icebergs, we get a negative SMB perturbation around into the Amundsen basin. And that's not additional melt, that's a reduction in the amount of precipitation that's happening there. So a reduction in the amount of snowfall that's offsetting the melt we're happening. But we think this is from the real peak year of that cooling. We don't expect the signal to be that strong for the rest of the simulation. And there's also then a question about how this affects the ocean circulation and the melt under those shelves. So as Jing showed us, we have this situation in UKESM where we can get warming coming under the Ross and the Filchner-Ronny. I don't have time to explain some of that, but a lot of that is triggered by freshening in front of the shelf. And you see that, so obviously we're putting a lot of water in front of the shelves. We put it in front of the Ross and it travels around in front of those other ones as well. We don't see that as a trigger, or it's not big enough to be a trigger in these simulations. So in this lower one here, you can just see that the warm water is trying to come onto the continental shelf, but it's not quite making it. So it's not, or at least I think it's a big enough perturbation, but it stays too close to the surface in these simulations. But this is against a pre-industrial control background. We would expect this, perhaps in a simulation where it was warmer, where we already had some freshening and melt coming from under those shelves, that this might be enough to trigger some of those other shelves further around East Antarctica to flip to warm cavities as well, if we did this under a warmer climate. So this isn't the end, because we haven't actually done the simulation yet when we take the surface of the shelf out as well, but we're getting there. But we have proved that we can do these simulations with UKESM in terms of putting all that water into the icebergs, seeing where it goes and what some of the wider system impacts will be when we do that. So watch this space for more simulations to come. Thank you.
Thank you, Robin. And again, just a reminder, if anyone has any questions for any of the presenters, please put them in the Q&A. We're now entering the last scientific thematic of the Ocean Ice Work Package 6 webinar that focuses on long-term ice, ocean and solid earth feedbacks. Our last speaker for today's seminar is Torsten. Torsten Albrecht is a senior researcher at Max Planck Institute of Geoanthropology and a senior scientist at Potsdam Institute for Climate Impact Research. He is an ice sheet modeler with a scientific background in physics, with expertise in ice sheet modelling and interaction with other Earth system components, such as the ocean, atmosphere, and the solid Earth. His work explores how freshwater forcing from ice sheets reshapes ocean circulation and stratification, and under which conditions this can feed back to ice shelf melt and ice sheet stability. Torsten co-developed the parallel ice sheet model with a focus on Antarctic ice sheet dynamics over glacial cycles, timescales, and the longer-term future, simulating processes like iceberg carving and continuum damage mechanics. He's involved in various international model intercomparison projects on sea level projections and tipping risks, and is leading the ice dynamics theme as part of the Earth Resilience Science Unit at the Potsdam Institute for Climate Impact Research. Today, Torsten will talk about the long-term effects of global warming on the interaction of the Antarctic ice sheet, ocean, and solid Earth dynamics. So thank you, Torsten. I'll hand over to you.
Yes, thank you for this introduction, Kylie. Right, so I'm going to talk about the even longer term effects of ice sheet, ocean, solid Earth interaction. And this is work at PIC together with Johannes Feldmann, Moritz Kreuzer, Ricarda Winkelmann, and others. And so when we talk about, we need this long terms if we talk really about stability of ice sheets and if we talk about tipping dynamics, for example. And when we talk about tipping dynamics again, we need to talk about feedbacks. And on this right-hand side graphic, we see many different feedbacks interacting with each other within the ice sheets or with different adjacent components. And we have like stabilizing feedbacks, but we also have self-reinforcing feedbacks, like the often call them positive feedbacks. And one example is the surface elevation melt feedback. So if you, for example, increase temperature, and if you have surface melt, this will lower the surface, the ice sheet surface. And as you may know from hiking or so, there's a lapse rate. So if you go to higher levels, the temperature will decrease, and this will lead to more warming and more melting and so on and so on. So this can be self reinforcing. But today I would like to talk about another self-reinforcing feedback, the melt stratification feedback between the ice sheet and the ocean. So we have seen similar graphics today before. So we have like comparably warm ocean at intermediate levels off the continental shelf of the ice sheet. And if we start like this warm water, if this intrudes into the ice shelf cavities, it can lead to melting, and the released fresh water again that can it can change the stratification and the mixing of the ocean, and this in turn can also have an effect again on the intermediate ocean temperatures. So if you trap energy in those levels, this can lead to additional warming, to additional melting, to additional freshwater release, and so on and so on. If you have seen some of the previous webinars, so there were like some experiments, model experiments with so-called hosing experiments, where you add just freshwater to the models and see how this affects the ocean, for example. So in this case, we really also investigate this kind of feedback between ice sheet and ocean on the long time scales. And we use a slightly different model here. So for the ice sheet, we have the parallel ice sheet model. And for the climate or the ocean, it's basically the MOM 3 degrees ocean model with a sea ice component. And actually, there's also an atmosphere component here. And the two model components basically exchange properties every 10 years. That's the coupling interval. So for example, between the ocean and the ice, temperature salinity is exchanged, and the ocean gets back in the conservative manner mass and energy fluxes. And right. And between like in this case, compared to UKESM, this is not a cavity resolving ocean model, but we kind of parameterize the ocean melt underneath the ice shelf with a so-called PICO model, the Potsdam Ice Shelf Cavity Module. So it basically translates changes in the ocean on the continental shelf or off the continental shelf into melting at the grounding line here. And this drives an overturning circulation. So it mimics kind of this overturning circulation in a box model extended to 3 dimensions. And the experiments we run here are also they are also simplified in the sense as the experiments we saw before. It's a 1% CO2 increase scenario, which stops after 140 years and stays constant. And we have like a pre-industrial run without additional warming standalone. And we have a coupled simulation between ice sheet and climate with full exchange of properties. And we have an intermediate step to kind of isolate this kind of melt certification feedback. So a coupled simulation where only the ice sheet is subjected to the warming. So it produces additional fresh water, which goes into the ocean and has an effect there. And then the ocean can feed back to the ice sheet again. Okay. So some of the results look like this. So if we, for example, have this transacts here, zonal mean temperatures in the ocean. So under pre-industrial conditions, if you add additional fresh water, you really see like a warming in the ocean all the way to the abyss and a cooling at the surface layer. So it's really like a very different stratification here in terms of temperatures. But if we, for example, consider an already warmed climate change scenario, then the effects are much smaller. So the warming is limited really to the Southern Ocean here and the upper layers. And we also can see this in terms of temperatures. So we have the temperature rise in the climate change scenario and only a little bit of additional warming due to this feedback. But if we have pre-industrial conditions, the additional warming due to this feedback, due to the additional meltwater is much stronger. So like about 0.6 degrees here in this case. And so we also came up with some kind of a metric for the feedback strength, which is basically the additional warming due to the additional meltwater compared to the freshwater fluxes. And the freshwater fluxes are similar in a way because the ice sheet in both cases experiences the same climate scenario, right? It's the same warming. And if we have a look to maps, so basically in pre-industrial conditions, we have like here in the Weddell Sea region, this open ocean convection area where the Antarctic bottom water formation forms. And if you then add this additional fresh water, this deep water formation is kind of limited very much. So this is basically also the dashed line, red dashed line here. While, for example, in the climate change scenario, it doesn't change so much, right? There's only a little bit deep water formation and it's not much reduced. So both effects of climate change and of additional meltwater feedback, they don't add up, right? So they have similar effects, but they don't superimpose, so to say. So this is important, like an important outcome of this study, where like really like a process understanding study in this case. There are some other effects. So if we talk about ice sheet instability, we often talk about the marine ice sheet instability. This is also a self-reinforcing feedback mechanism taking place here at the triple point between bedrock, ice sheet, and ocean. And as we learned already in this, for example, also in talk by Robin, so buttressing of ice shelves play an important role here. So this is something that we also investigated in a standalone ice sheet simulation here. So this is a different experiment. It's basically the historical spin up from 1850 to 2015. And then we keep the climate constant into the future. And what happens that in some cases, if you keep running it for millennia, basically, some of those simulations actually tip in terms of that the West Antarctic ice sheet, or in this case, the Amundsen Sea region, becomes afloat, and this orange areas are the ice shelves which form over a long time scale. The green line is the present day or the pre-industrial grounding line, and then you see how this grounding line kind of retreats into the interior of the ice sheet. Especially as we have like this retrograding slope bed conditions here in this case. What's interesting here, there's no calving applied in this simulation, but if we now, and we use, for example, in our simulations, a calving parameterization, which takes into account the stress state of the ice sheet and the ice shelf. So there's some non-local effects here due to the geometry of the ice shelf. So the exposure of the ice shelf, the confining geometry is taken into account here, and it's also like a nonlinear effect basically. And what we can see here is that there's a free parameter k in this case. So if we increase this parameter, at some point most of the ice shelf is basically gone. So it's a little bit binary here in this case. But if we add another ingredient, and this is viscoelastic beta formation in this case, this adds a stabilizing feedback, the so-called, sometimes it's called sea level feedback or near field sea level feedback. Basically, if you have like grounding line retreat and a thinning of the ice thickness, the bedrock will uplift and this stabilizes the grounding line again. And if we go down here in the panels towards low viscosities, towards a thin elastic lithosphere, we really can see this kind of stabilizing effect. And at the same point, it's not only the grounding line retreat that it is kind of stabilized or halted. It's also that pinning points due to the uplift form and stabilize the ice shelf. That we have some, situations where some smaller ice shelves, which add buttressing, can remain. And this is interesting on the long-term perspective here in terms of stability. Right. So if we have really considered this long-term simulations, we really see a big difference actually between simulations that where like a strong calving and high mantle viscosities are applied to, as compared to low viscosities and a weak calving. And especially this region, the Amundsen Sea region, it's very likely a region of very low viscosity. So it's also very likely that this kind of effect on the long term may help a little bit to stabilize this region. But to what extent, and compared to the high emission warming scenarios, that's another question then. But so far that's it from my side.
Thank you very much, Torsten. We're now entering the last part of the webinar, which is the Q&A and discussion section. And so I have some questions for the presenters. The first one is to Jing. I was wondering, what are the changes that happen outside of the ice shelf cavities?
Oh yeah, I can I share my screen?
Yeah.
Okay. I think I just show it briefly. So we can see, well, if you compared the two experiments, actually in the interactive ice sheet model, though it produce less total amount of fresh water than the static ice sheet run, actually can see there's like more freshening outside of the cavity, which means so I assume it's because of the depth of the freshwater injection into the continental shelf sea are different in the two experiments. Because the ice is thinning, well, it's shallower, so the freshwater gets into a shallower Southern Ocean shelf sea, so it produces like much more fresher upper ocean of the shelf sea in the interactive ice sheet run. And this also, I say, results in a warmer mid-layer ocean in the interactive ice sheet run. So if you compared this to white line in the bottom panel, so the white line is 0.5 isothermal. You can see it's shallower in the interactive run, so which means like more warm water occupied the deep ocean. in the interactive round. So I would say, well, some people may interpret our work that there's less base amount from Antarctica, so we can care less about it. Though no, that's not how you interpret. So, and I would say there's actually warmer in the upper ocean in the when it coupled with the ice sheet.
Okay, thank you. And now a question for Yavor. How important is the choice of defining the dense bottom layer around Antarctica? Should the definition change as climate changes under increased carbon dioxide?
Thank you for this question. This is indeed the case that we see in the ramp-up experiments. The thickness of this densest layer shrinks dramatically, and we end up seeing dense water that's formed on the shelf, but it is lighter than before. So on one hand, we have less dense water forming, but we also have dense water that's lighter than before. It's still allowing a communication between the shelf region and the abyss. So it may be useful to have a varying definition of what this neutral density surface that connects the upper ocean to the abyss should be. And there are other criteria that can be used to define these layers or water masses, as we call them. For example, in a model, we can look at how layered each layer is within. So as we say, how stratified, because when the deep water forms on the shelf, it's formed by vertical convection, which homogenizes that volume of water in the vertical. So it ends up being less stratified, less layered within itself. And that property is preserved as the water moves towards the abyss. In the real world, or in a model that has biogeochemistry enabled, we can also look at oxygen as an indicator of recently formed precursors to Antarctic bottom water, because during the process of surface convection, the water is enriched with a lot of oxygen. So that could be a useful tracer for tracking this communication between the surface mix there and the abyss. So thank you for raising this point.
Yeah, thank you. And now a question for Robin. Do you think it's possible that the Ross Ice Shelf could collapse like this in the near future?
That's a really good question. It's possible. I think is probably the answer. So we've done quite a few simulations with UKESM now that show this flip of the Ross to a warm water cavity like Jing was showing. And depending on the climate forcing, we've had that happen as early as like 2040 or under, say, 3 or 4 degrees of global warming, which is sort of entirely possible. And we think the physical mechanisms for how that ends up happening are pretty robust. So even if the timing or some of the, I mean, UKSM has biases, any climate model does. Even if some of those are in action, we think the mechanisms we found are robust enough that flip to warm water is likely to happen. In terms of the shelf breaking up completely so suddenly, we know there's potential for sort of ponding and hydrofracturing to happen under these warm scenarios as well after 2100. So that's quite a bit later than we were talking about the shelf warming happening. And that's much less certain in terms of how well we're modeling the processes involved. So that part of it is less certain. And then there's lots of iceberg physics that we're not doing here in terms of how big those icebergs should be, and thus whether they should ground immediately and not actually spread out so quickly. So then that part needs a lot more of the work that, say, Yavor's been involved with in looking at some of the iceberg modeling in ocean ice. So there's different answers to that. We're definitely at risk of melting it a lot, like Jing was showing. I think the the catastrophic collapse is much more one of these low likelihood but very high impact situations.
Yeah, thank you. Okay, we've got time for a few more questions, so just a reminder to send them in if you have any for our presenters. The next question I have is for Torsten. Should model projections of future sea level contributions from ice sheets include the solid Earth feedbacks? And how relevant is it for the next 100 or 300 years?
Yeah, thanks for the question. Yeah, we discussed this a lot now also in the community when it's about sea level projections in terms of ice sheet model intercomparison framework. Because if you go to, let's say, 100 years, it may not have a big impact. But if you talk about sea level projections, really like to 2300, you really see a quite diverging effect if you have solid Earth sea level feedbacks considered or not. So there are some recent studies that say that, like, on this timescales, you can have a reduced sea level impact or contribution from Antarctica by 20 or even 40%. That's quite a lot when we talk about like meters of sea level rise. So it seems to be a very important effect for certain regions on the long timescales. That's why I think the recommendation would be, yeah, it's important to include this somehow. And there are different components of including it. There's a viscoelastic component, there's a gravitational component, and so with different complexities, it's an important mechanism on the long timescales.
Okay, thank you. And now a question for Tony. After nearly 3 years working with the group in Work Package 6, I'm wondering if there's one story or memory that really stands out for you in working with this group.
Tricky question. I think what struck me is that there's kind of two sorts of ways in which the project works. There's the kind of formal steering committee, work package leads, members of the work package, and there's those communications, which are a bit boring and kind of fairly routine. But what's a lot more exciting is when the individual postdocs get together and exchange ideas. And that's perhaps where it's been most exciting to see that two people are working on similar topics or have come to similar sort of conclusions independently outside of this structure that we've imposed on the research. So that's probably where I can't think of a specific example. What came up in the last annual meeting is there are a lot of people, as you've heard today, and also in previous presentations, using various types of ocean model, but are all slightly forced in slightly different ways. Experiments aren't exactly comparable, but some of the results appear to be comparable. And that's an exercise we want to do in the immediate future, is to try to bring those people together to see, although the models are set up differently, they're different models, slightly different scenarios, what's the kind of underlying truths that are emerging.
Yeah. Okay, great. Thank you. That answer probably leads well to what I think will be the last question for the webinar. And the work you presented today focuses a lot on future projections. So I'm wondering, how has modelling and future scenarios in this project helped you to go beyond observations? For example, to test new theories or to explore causation to enable us to have enhanced forecasts. And that can be for anyone that feels like they want to respond on that topic.
I think there's one aspect in that while the observations are fantastic, in particular since satellite observation, the ice sheets have become important. I think Torsten mentioned they only capture certain processes because we know that some processes that may be important only trigger at certain levels of global warming. So in which case observations, we can try to tune our ice sheet models and try to reproduce reality, but we know that there's some things that may occur in the future that we just haven't got observations for, and we have to rely entirely on theory to try to represent those processes.
I could maybe also add an aspect that we learned over the last years. Like, for example, if you talk about let's say, present day observations, which are really great, and define also you can compare your model results of the present day observations. But then if you keep them running, they can really diverge over long time scales. So it's not only the state, it's also the change rates, for example, that matter. And we are getting better and better with observations to constrain our models in that as well. So this helps a lot. So even though under present day conditions, model simulations look similar, they can have a very different outcome on the long time scale. So that's also an interesting insight how this is connected.
Yeah. Okay, excellent. Thank you, everyone. Well, on that note, I would like to warmly thank all of today's presenters for sharing their research from Ocean Ice Work Package 6, and to all of the attendees for taking part in this webinar. A recording of the webinar will be available on the EPB YouTube channel in the coming days. So thank you again, everyone, and I wish you a pleasant afternoon.